Hello, welcome to this MOOC on principles of CDMA, MIMO, OFDM wireless communications. So today we are going to start looking at the bit rate performance of a wireless communication system. Previously we have looked at the bit rate performance of a wireline communication system, which could be modeled as a simple AWGN, that is an additive white Gaussian noise channel. Now let us start looking at the bit rate performance of a wireless communication system, so that we can compare the performance of a wireline and wireless communication systems. So we are going to start looking at a bit rate BR of a wireless communication system. And as we said previously, in a wireless communication system there is fading due to multipath nature of the propagation of the signal in the wireless communication environment. So wireless communication system there is basically fading. The signal is fading in nature because of the multipath propagation nature of the wireless channel, and therefore the channel can be modeled as follows. Let us say I have a transmitted signal X, and this signal is now transmitted over the wireless channel, and as we know that this signal undergoes fading, therefore it is multiplied by the fading channel coefficient H, and now at the receiver as before there is the additive noise N, and finally we have the received signal Y. So the new aspect of this wireless communication system is this fading nature of the channel, which is modeled by the fading coefficient. This H is the fading coefficient. As usual, we are assuming this N to be Gaussian noise or white Gaussian noise with 0 mean, that is mean 0, and variance or basically power variance equal to sigma square. And therefore, the channel or the model for this wireless communication system, the model for this wireless system can be written as, we have Y, that is the received symbol, equals H X plus N, where Y is the, so where Y, this is the received symbol, X is my transmitted, N is the noise, and most importantly my H is the fading coefficient. And also we said that H can be modeled as A e to the power of j phi, where A is the magnitude or the amplitude of the fading coefficient and phi is the phase of the fading coefficient, and we also said that A follows the Rayleigh density or the Rayleigh distribution, right. This is the fading channel coefficient. So I have Y equals Hx plus N, where H is the fading channel coefficient. Therefore, now if I look at this signal model, I have, what do I have? I have Y equals Hx plus N. So this received signal S, so this signal X is multiplied by the transmitted signal X is multiplied by H, and therefore I have the received signal power or received power equals magnitude of H square times the transmitted power, because the signal is multiplied by the transmitted signal X is multiplied by the fading coefficient. I have the received signal power is equal to magnitude of H square times P, but H is equal to A e to the power of j phi, which means magnitude of h equals A, and therefore, we have the received power equals A square times P, right, and therefore, the received SNR or the fading SNR, which I am going to denote by SNR F, this I am going to call as the fading SNR. SNR F is basically the received power A square P divided by the noise power sigma square, which is A square P divided by sigma square, but P divided by sigma square is our definition of SNR. So, therefore, this is A square times SNR, right. So, because of the fading nature of the wireless communication channel, the fading SNR F is A square times the SNR, which is P, the transmit over P divided by the noise power sigma square, where A is the magnitude of the fading channel coefficient H. And now, what we have is, as you remember from the bit error rate expression derived for BPSK modulation, from the bit error rate derived for BPSK modulation. What do we have? We have bit error rate is q of square root of SNR, but here the SNR is the fading SNR, because the transmitted signal is multiplied by the fading coefficient H. Therefore, the bit error rate is q of square root of the fading SNR F, which is also equal to q of square root of A square times SNR, where SNR equals P over sigma square. Therefore, what you can see is that this quantity under the square root, this depends on the magnitude of the fading coefficient, this depends on the fading coefficient H. This depends on the fading coefficient H, and since the fading coefficient H is random in nature, therefore, this fading SNR, that is A square times SNR, is also random in nature. Hence, the resultant bit error rate q of square root of A square times SNR is also a random quantity, because A, which is random in nature. Hence, therefore, this entire quantity, this is basically, this is a random quantity because of the random nature of the fading channel coefficient. This is a random quantity which arises because of the random nature of the fading channel coefficient, right. And therefore, to find the average bit error rate, in order to find the average bit error rate, one has to average with respect to the distribution of the fading channel coefficient or the distribution of A. To find average bit error rate, therefore, to find average BER, we have to average with respect to the distribution of A. We have to average with respect to find the average bit error rate. We have to take this function, because this function is a random quantity, because it depends on the random channel amplitude, that is A, right. So, this is random in nature. Therefore, to find average bit error rate in this fading channel condition, one has to average with respect to, one has to average this expression with respect to this, the distribution of the fading channel coefficient amplitude A. And therefore, and we already know that the distribution of A, that is the fading channel amplitude, it follows the Rayleigh distribution. You can look at the previous modules. This is given as 2A e to the power of minus A square, and therefore, the average bit error rate, is equal to 0 to infinity q of square root of Sn A square times square root of SNR times Fa of A dA. So, what I am doing? I am taking this random bit error rate, I am multiplying this with the distribution of the fading channel amplitude A, and I am averaging it by integrating it from 0 to infinity. That will give me the average bit error rate, average with respect to the distribution of the fading channel amplitude, that is A. Or in other words, this is equal to 0 to infinity q of square root of A square SNR times substituting the expression for Fa 2A e to the power of minus A square dA. And now, I am not going to evaluate this expression explicitly in this module, because evaluating this integral is slightly complicated. So, I am not going to evaluate it right now in this module. I am going to skip this derivation at this point, and I am going to give you the result directly. But for the more advanced viewer who is interested in knowing the complete derivation of this expression, you can look at subsequent module to get it. So, for a sort of a beginner who is probably not interested in all the details, all the minor details involved in this derivation, you can simply follow the result, and the result is given as half 1 minus square root of SNR divided by 2 plus SNR. So, the average bit error rate, the final result, which I have not derived here thoroughly, for which I have not given the complete derivation here, I will do this in the next module. So, the expression, that is the expression for the average bit error rate, when I average this bit error rate over the distribution of the fading channel coefficient A, is given as half 1 minus square root of SNR over 2 plus SNR. So, let me remind you, this is the expression for average bit error rate of BPSK modulation in a fading wireless, in a Rayleigh fading wireless channel. So, this is average bit error rate for BPSK modulation, BPSK in a Rayleigh faded or Rayleigh fading in a, this is the average bit error rate for BPSK modulation in a Rayleigh fading channel. This is half times 1 minus square root of SNR by SNR over 2 plus SNR. Correct. This is the final expression that we derive. And let us do a few examples to understand this better. For instance, let us again do the example similar to what we have done in the case of a simple wire line or a simple AWGN based communication channel. So, compute the bit error rate of a wireless communication system. So, we want to compute the bit error rate of a wireless communication system for SNR equals 20 dB. So, we want to compute the bit error rate, that is the SNR dB SNR equals 20 dB, which means 10 log 10 of SNR equals 20, which implies that log 10 of SNR equals 2, which implies SNR equals 10 raised to 2, that is 100. So, if the dB SNR is 20, that means the actual SNR is 100, and now my bit error rate I have to substitute in my formula for a wireless communication channel, that is half 1 minus square root of SNR divided by 2 plus SNR, which is equal to half 1 minus square root of 100 divided by 102, which is equal to 4.92 into 10 to the power of minus 3. So, the bit error rate in a wireless channel at 20 dB SNR is 4.92 into 10 to the power of minus 3. Right. So, what we have done is we have computed the bit error rate in a wireless communication system with fading for BPSK transmission at an SNR of 20 dB, and the answer is 4.92 times 10 to the power of minus 3. Now, let us do another example. Let us do another example to understand this better, and we would like to compute SNR, the dB SNR required for a wireless communication system. For a wireless communication system for a bit error rate equals 10 to the power of minus 6. That is, what is the SNR in dB in a wireless communication system required to achieve a bit error rate of 10 to the power of minus 6. So, this is the reverse problem. We are required to calculate, previously we are given the SNR and asked to calculate the bit error rate. Now, we are given the bit error rate and asked to calculate the required SNR in dB. Therefore, we have 10 to the power of minus 6 equals half times 1 minus square root of SNR divided by 2 plus SNR, which basically implies that SNR divided by 2 plus SNR equals 1 minus 2 into 10 power minus 6 whole square, which implies that SNR equals twice 1 minus 2 into 10 power minus 6 whole square divided by 1 minus 2 into 10 power minus 6 whole square equals, which equals basically 4.99 into 10 to the power of 5, and SNR dB and the dB SNR equals 10 log 10 SNR, which is equal to 10 log 10 SNR, which is equal to 56.98, 10 log 10 SNR, which is 56. So, what we calculated is that to achieve a bit error rate of 10 to the power of minus 6 in a wireless communication system, we need an SNR of 56.98, that is approximately 57 dB, approximately 57 dB. And if you remember from our previous discussion on the AWGN, that is a wireline communication system, remember from our previous discussion that for 10 to the power of minus 6 bit error rate in an AWGN channel, we require an SNR of approximately 14.19 dB. For an AWGN or a wireless channel, GN or wireline channel, the corresponding SNR required to achieve BR equals 10 power minus 6 is 14.19 dB. For a fading wireless channel, as we have just seen previously, it is 57 dB. Therefore, approximately for a wireless channel, how much more SNR do we need to achieve 10 to the power of minus 6 bit error rate? Therefore, for a wireless channel, the extra SNR in dB is my 56.98, which is approximately 57 minus 14.19, which is 14, and that is equal to approximately 43 dB. So, you can see this 43 dB is the extra SNR that is required in a wireless channel. Approximately 14 dB is required in a AWGN or wireline channel. So, over that, on top of that, additionally you require an SNR of around 43 dB in a wireless channel to achieve the same bit rate. So, you require, so if the noise power is the same at the receiver, you require 43 dB more transmit power in the wireless channel to achieve the same bit rate of 10 power minus 6. So, there is a huge increase. So, there is a huge increase in required SNR to achieve same bit rate, equal to 10 power minus 6 in our So, what we are saying is, in a wireless channel to achieve a bit rate of 10 power minus 6, we need 43 dB more SNR approximately, and if the noise power is, remember SNR is ratio of signal power to noise power. Therefore, if the noise power is same in both the systems, it means transmit power has to increase by 43 dB. 43 dB, if you convert it into a normal scale, 43 dB is in log scale. In normal scale, it means 10 to the power of 4.3 times more power is required in a wireless communication. So, that is a huge amount of extra power that is required in a wireless communication system. So, it requires a huge increase in the SNR to achieve the same bit rate. And why is this the case? Let us examine why is this the case. Let us examine the reason for this, and if you look at the bit rate expression, you have bit rate equals half times 1 minus square root of SNR divided by 2 plus SNR. I can also write this as half times 1 minus, now I will bring the SNR into the denominator. So, I will write 1 by 1 plus 2 over SNR, which is also equal to half 1 minus 1 plus 2 over SNR to the power of minus half. Now, I am going to use an approximation at high SNR. At high SNR, if SNR is large, then 1 over SNR is a small quantity. Therefore, I can write this as half 1 minus half times 2 over SNR, which is equal to half times 1 minus 1 cancels, which have half times 2 over SNR, which is basically equal to 1 over 2 SNR. So, the bit rate is decrease is proportional to 1 over SNR. So, in the wireless communication system, the bit rate is decreasing at 1 over SNR. So, if you look at the net result, BER in wireless is proportional to 1 over 2 times SNR. However, if you remember the bit rate in AWGN or the wireline communication system, this is equal to approximately q of square root of SNR, which you remember this is equal to half e raised to minus half SNR. Therefore, in a wire line communication system, it is decreasing as exponentially with respect to SNR. So, if you look at the bit error rate in a wire line communication system, bit error rate in a wire line communication system is decreasing exponentially. Bit error rate in a wire line communication system is decreasing exponentially with respect to SNR, while in a wireless system it is only decreasing as 1 over SNR. So, there is a huge gap in the bit error rate of a wire line communication system versus a wireless communication system. This is because in a wire line system, while it is decreasing exponentially, in a wireless communication system it is only decreasing as 1 over SNR, and that is the very important difference between the performance of wire line and wireless communication systems. So, wireless communication systems have a very high bit error rate because of the sluggish decrease in the bit error rate versus SNR, which is only decreasing as 1 over SNR, and that is the result you see. In order to achieve the same bit error rate in a wireless communication system, you need a huge amount of extra transmit power, that is at 10 to the power of minus 6 bit error rate for BPSK, you need approximately 43 dB more transmitted power. Alright. So, let us do another simple example to understand this better. So, another example is now using our approximate formula, using our approximation that we have recently developed, using the formula for approximate bit error rate in the wireless system, using the formula for approximate bit error rate, calculate SNR, again calculate SNR for bit error rate equals 10 power minus 6 in our wireless system. And for this purpose, what do we have? We have 10 to the power of minus 6. Remember, now we have to use the approximate formula, which is approximate formula is, if you look at it, 1 over 2 SNR. So, that is equal to 1 over twice SNR, which means SNR equals 1 over 2 times 10 to the power of minus 6, which is equal to 0.5 into 10 to the power of 6. This is equal to 0.5 into 10 to the power of 6, and the SNR in dB equals 10 log 10 0.5 into 10 to the power of 6, which is equal to 56.98, that is approximately equal to 57 dB. So, this is the same answer that we get for the dB SNR that is required to achieve a bit error rate of 10 to the power of minus 6 in a wireless communication system. So, therefore, we have two expressions for the bit error rate of a wireless communication system. Bit error rate, so in this module let us summarize the bit error rate of wireless bit error rate of a wireless system. The first formula is the exact formula. The exact expression for the bit error rate equals half 1 minus square root of SNR divided by 2 plus SNR, and then we also have an approximate expression. In the approximate expression, the bit error rate is 1 over twice is SNR. We have bit error rate equals 1 over twice SNR. So, we have two expressions. One is the exact expression, that is bit error rate equals half 1 minus square root of SNR divided by 2 plus SNR, and the approximate expression is bit error rate equals 1 over twice SNR, and this is especially, this approximate expression is valid at high SNR, that is at high SNR. Remember, we employed the assumption that 1 over SNR is a small quantity close to approximately equal to 0 or close to 0 to derive this approximation. So, this approximation 1 over 2 SNR, that is the bit error rate for a wireless system is equal to 1 over twice SNR, is valid at high SNR. So, these are the two expressions that we have derived for the bit error rate performance of a wireless communication system. So, we will end this module here and take up other topics in subsequent modules. Thank you very much.